Okay, so here we are in our momentum unit. We've learned how to apply conservation of momentum, and we've even seen that in elastic collisions, energy is also conserved. We can use that equation from our equation sheet, as shown in the last video, and solve for two velocities in a single problem because we have two equations. So we were applying conservation of momentum and conservation of energy at the same time. Now, just as we've been doing throughout the semester, we can look at what we're doing now and look back to prior time periods and keep utilizing that old information, those old concepts, and they're really, I guess it can be a difficult thing, but the really powerful thing is being able to understand when we can apply those different concepts, when are those valid things to do, and when are they not valid. And so let's look at some of these examples here, and so we can figure out when we can apply conservation of momentum and when we can apply conservation of energy. In this first example, we have a bullet colliding with a stationary block, becomes embedded in the block, which then slides off the table and falls to the floor. Momentum is conserved during the collision. And we know that because momentum is conserved in elastic collisions and inelastic collisions. But is energy conserved during that collision? Well, the bullet becomes embedded into the block, and so that right there tells us that it is an inelastic collision, because we know automatically, we don't have to do any calculations to know it's inelastic because it's perfectly inelastic, so easy to identify. So if it's perfectly inelastic, energy is not conserved during the collision. Talking about kinetic energy, of course. The energy of the universe is still conserved, just the energy in the system, not conserved. Some of that kinetic energy is getting converted into thermal energy and sound energy through the deformation of the materials. But in any case, we can only apply conservation of momentum to the collision, not conservation of energy. But then, while the block is falling to the floor, energy is conserved for that part, and so we could look at it, the falling part, as from the moment it leaves the table until it gets to the floor, till it's just about to reach the floor. We could look at that easily from a conservation of energy perspective. We could also look at that part where it's flying off the table from the moment it leaves the table till it's almost going to hit the floor as a projectile motion problem, a two-dimensional kinematics problem. All right. Now in this second problem, we have a pendulum pulled back to a certain angle and released. And when it gets to the bottom of the swing, it collides with a soccer ball. Okay, and so in some ways, this could be thought of as a very simple model for a leg swinging and the foot striking the soccer ball. Of course, there's a lot more to it, but in any case, what's going on here? Well, while the pendulum is swinging, conservation of energy principles can be applied, and then while the collision is happening, conservation of momentum principles can be applied. Now, the pendulum collides with the soccer ball. They don't stick together, so we don't know, it's unclear, we don't know if energy is conserved during the collision. There was no indication given either way, so we don't want to assume that it is. So we will only apply conservation of momentum principles to the collision part. All right, and so those were just some generic examples so we could talk through. But next, we're going to go through an actual example of something where you can use one principle in one part and use a different principle in another part. Here we go. We've got a 5 gram bullet traveling at 300 meters per second, embedding in a 500 gram stationary target. This should sound familiar. We've done a lot of problems with this bullet and target. The bullet and target move across a level frictionless table before striking a spring, which has a spring constant of 1,000 newtons per meter. And how much can the spring be compressed? All right, so we think about here. It says it strikes and is embedded in, and so that is a collision. And so right away we want to be thinking about conservation of momentum. Okay. And it's a perfectly inelastic collision, and so not conservation of energy. Okay, so that's stage one. And then we go and we think, all right, the bullet's sliding across a frictionless table, striking a spring, and the spring is becoming compressed. Oh, we remember that conservation of energy principles work really well for a before and after involving a spring. I mean, we can use that for lots of problems without springs as well, but the conservation of energy should work well for that. And so we go ahead and draw a diagram here. Well, let's see, we'll say to the right is our positive x direction, and we've got our 5-gram bullet moving along, and we'll call this initial velocity 300 meters per second, and we've got the block, which is 500 grams, and its initial velocity is 0, and we're going to apply well, that's our initial state. And then we're going to look at what happens when after the collision. So this is our final state. The mass is 505 grams, and the final velocity, we don't know. Okay, and so this right here is stage 1. Conservation of momentum. And if we keep going, we can say, all right, well, what happens then? Then the block and the bullet together slide across the table, and they get to a point where they're up against a spring attached to the wall, or some it's firmly in place, so the spring is compressing as the block hits it. And then this is going to be our final. Okay, now we have 2 finals. So this is the final for one part. I'm sorry, this is the final of the second part. This is the final of the first part, but it's also the initial for the second part. And so let's see if we can clear that up a little bit. Okay, so we can say that this is our initial for part 2, and this is our final for part 2, because then we can make this our stage 2, and there's no reason to apply conservation of momentum here. We can't really analyze the spring's velocity before or after. It's 0 before and after. It moves a little bit in the middle. And so conservation of momentum doesn't make any sense, but conservation of energy is super easy to apply to that. And so we can look at this in 2 stages. All right, let's look at stage 1, which we'll do in green. Conservation of momentum, 5 grams times 300 meters per second, plus 500 grams times 0, wasn't moving at all. And then afterward, the 2 things are stuck together, so we'll just treat them as a single object with a single final velocity. And then we get 1500 gram meters per second equals 505 grams times VF. Divide both sides by 505 grams, and we get a final velocity, and this is a vector. The final velocity of 2.97 meters per second. It's a positive value, which means it's moving to the right. All right. This is our initial velocity for stage 2. Okay. Now we need to do our stage 2 calculations. We're going to take this up there. And so, let's see, conservation of energy. Oh yeah, that big long equation. The gravitational potential energy plus the spring potential energy plus the kinetic energy plus the work by non-conservative forces is equal to how much gravitational potential energy it has afterward, how much spring potential energy it has afterward, and how much kinetic energy it has afterward. All right, now we got to think through this. Say, okay, well, call this level, the place where gravitational potential energy is 0, and so we'll get rid of both of those. It comes to a stop, and how do I know that? Well, I'm trying to find the maximum distance the spring can be compressed. If it were still moving to the right, the spring wouldn't be at its maximum compression. And if it were already moving back to the left, the spring would not be at its maximum compression. So that's 0. The spring is not compressed at all in the initial part. Okay, the object is still over here, hasn't touched the spring, so that's 0. And then the other part is that there's no work done by non-conservative forces. Okay, we go into this and we look and we say, okay, well, there's a normal force acting and there's weight. The normal force doesn't do any work because it's perpendicular to the displacement, and so the normal force doesn't do any work. And then for part of the time we have a spring force that's capital F sub s, and so that is also a conservative force. So the only non-conservative force is the normal force, and it doesn't do any work, so that is 0. So then we simply say 1/2 mvi squared equals 1/2 k delta x f quantity squared. We fill in our values, and I'm going to use SI units here, so 0.505 kilograms times our velocity that we found. And so this is actually going in right there. Square that equals 1/2 times 1,000 newtons per meter times delta x f quantity squared. All right, and doing the algebra here, we get delta x f equals plus or minus the square root. If we multiply both sides by 2, the 1/2 goes away. Then we have 0.505 kilograms times 2.97 meters per second. Oh. There we go. Quantity squared. Divide that by 1,000 newtons per meter. Take the square root of both sides, and we get delta xf equals 0.0667 meters. I picked the positive root because the delta x is going to be to the right, and the right is our positive direction. And then we could also say that this is 6.67 centimeters. And that is our final answer. Okay, so again, applied conservation of momentum to the part where they're colliding, applied conservation of energy to the part where the object was sliding along and running into a spring. So we had initial here and final here, and then this final became the initial for the next part. And so this was the initial and the final for the conservation of energy part.